Hi, everyone. Back again with another episode of Inside Philip's Brain. As part of my little series here exploring different aspects of AI, today I want to talk about how we might think about AI as fitting observations to a highly complex distribution. In previous sessions, we explored how AI fundamentally is a model that relates inputs to outputs via statistical patterns that the model has learned by looking at lots and lots of training data and incrementally adjusting internal variables or weights to represent those statistical patterns, which, after being sufficiently trained, it can use to predict new outputs from new inputs that are consistent with those patterns it's learned. We also explored how generative AI is basically a random walk through those learned patterns. The magic is in the learning and in the memory that the model has of what it's learned. So, how should we think about that memory that the model has? Well, one analogy is to think of it as a distribution that is being fitted to a curve. I'll use the simple example of a model meant to predict the price of a house, which admittedly is a favorite regression example. In the simplest version of this model, the input might be just the square feet of area in the house, and the output will, of course, be the predicted price. Now, this is crazy simple, but any of you who have shopped for a house know that price per square foot or price per square meter is a commonly used metric to compare prices across different houses. A basic mathematical method that many of you are probably familiar with is linear regression, which takes a bunch of real-world observations and finds a straight line that goes through the center of those observations as closely as possible, i.e., it fits the line to the observations as closely as it can. If the observations are incredibly consistent, then they will all be right on that line. But if they're a bit squishier, then a scatter plot of them looks more like a cloud, and the regression line runs through the center of the cloud. Now, price per square foot is a straight line. It's a linear function. We can easily find it by simply dividing the actual sale price of a house by its square feet of area to determine that house's price per square foot. And if we do that for lots and lots of houses of various sizes and locations and ages, etc., and then we average them together, we end up with an overall average price per square foot. Now, basically, the actual data of the sizes of houses and how much they sold for is our training data. We go through, we run that simple model I just described, and we come out with a single number. And let's just say that number turns out to be $1,000 per square foot, just to keep it simple. Now, all that our model needs to remember from what it learned is the number 1,000. That 1,000 is the memory that stands for all the prices of the houses it has seen. So it learned that statistical pattern, as simple as it may be, that relates the input to the output by looking at training examples. Now, to use the model, after it's been trained to learn 1,000, we just feed in the square feet of some new house coming on the market, and the model multiplies that by 1,000 to spit out its predicted price in dollars, of course. In reality, price per square foot is not that consistent. Now, for instance, it might vary based on the size of the house. Perhaps the price per square foot goes down for larger houses. Then you'd need a curved line rather than a straight one. Maybe the price per square foot goes down for larger houses until it reaches a certain level where there are very few houses of that enormous size and there's limited supply on the market. And the buyers of those houses, of course, are super price insensitive, as we might imagine. So the price per square foot actually starts to go back up again. Now you need a really curvy line, and you need a lot more complexity to represent that curvy line in the model's memory, not just a single number 1,000. Of course, we all know that houses are valued on much more than their square feet of area. If the house is on a big property lot, it's likely to be more valuable than a house of the same size that sits on a smaller lot. So now let's add a second input to our model. So the model takes in the size of the house and the size of the lot, and is no longer a line, but now it's a surface if you graph it. The model is operating in 3 dimensions instead of 2. Of course, there's even more that can affect the price of a house, such as the number of bathrooms, how many cars fit in the garage, how old is the house, what's the quality of workmanship on the house, is the lot flat or on a hillside, is it prone to flooding? What's the quality of the view from the house or from the backyard? Can you hear highway noise? Does it have a pool? What's the crime rate in the neighborhood? What's the level of affluence in the neighborhood? How good are the local schools? Is the house at risk from climate change? How's the economy doing right now overall? How's the housing market doing right now? What are local taxes like where this house is? And so on and so on and so on. To capture all of those, you now have to have a model operating in like 20 dimensions, just using the examples I just rattled off. And we can imagine that that set of examples is far from exhaustive. So it's not just the number of inputs that becomes more and more complex, the more accurate you want your model to be in its predictions. There may be a lot of subtle interplay between those inputs. In particular, an input might influence the output a lot unless some other variable comes into play, for which that first variable, in that case, that first variable gets less important. For example, people might really care about having a new house. Like that's what they want. They want a new house until they see one that has a view that's to die for. And then suddenly they don't care how old the house is. Now, for us to construct a model that captures all those variables, including potentially differently curved lines for each variable, and including all the ways that any variable might influence another variable, and then running some kind of multivariate regression to figure out how to represent the impact and the interactions of all those variables would be massive. But this is akin to what machine learning does. Neural networks, the basic building block of machine learning models today, are very good at representing these extraordinarily complex relationships, which they do via the weights, which we talked about before, attached to the nodes in the network. Those nodes might be called neurons or activation units. Doesn't really matter. But those weights that I mentioned previously, they get nudged around, as we talked about, during the training. Until they come to represent the patterns inherent in the training data, including very complex patterns and patterns that represent that influence other layers of the pattern. So the memory of the model is that set of relationships that it has learned and stored as weights, and it's no different in concept from the extremely simple memory of $1,000 per square foot, although of course generally dramatically more complex. Now, we as humans can easily conceive of the concept that there are a whole lot of considerations that go into buying a house. And we'll even traverse those considerations in our brains as we make a decision on whether to buy a house or what we think a fair price for that house might be. Yet, while the overall construct is simple, the internals are highly complex and frankly impossible for us to comprehend in a conscious way. Now, some AI models deal in billions of dimensions with all kinds of interplay between the variables. So while the overall idea of the model is not hard to grok, actually comprehending how the model works internally in some conscious way is impossible. And that's a key part of the magic of AI, why it feels that way. So I hope that thinking about AI models as fitting to very complex distribution helps take some of the mystery out of it while still paying homage to the incredible sophistication and complexity and frankly, the incomprehensibility of them. Thanks, everyone. That's my thought for now. I'll be back again soon with more. Take care.